Hey, how y'all doing today? Okay, so you heard me, and I'm hoping that if any of you need to talk to me or at me, someone will test that out now because, volume. Okay, I haven't heard anything, but okay, well, I'm going to proceed as though everything's perfect. And if there is a problem and you have a question, comment, opinion, etc., want to share something, and if you're saying it frantically and everyone else in the class can hear, but I can't, haha, that would be unfortunate, but you could always put something in the chat. So what I'm going to do is start by sharing a screen and maybe focus on then the last couple of things we're going to do this term. Okay, so maybe sort of looking at the syllabus would be a good call. Oh yeah, there's this final. You should show up for the final on Thursday of this week. The final exam is Thursday, 4:10 till 6 o'clock p.m. And I don't think I have it on the syllabus, but it's in Baker Science. And then that is, I guess, room three, 130, 113. But I'll make sure I make that more clear and visible. But yeah, you should all show up there at the place for the exam. If we're looking about what happens on what day, today, chapter 9, the intention is to also do chapter 9 a little bit and then 10 a little bit on Tuesday. Those are both, in my mind, really key. And then because we have the review from a past term, I might encourage you to watch the video. And chapter 11, sections 1 and 2 are really also key and central to the class. It shouldn't take too long to do chapter sections 11, 1, and 2. So we'll have plenty of time for review, I think, going over those sample exam questions. And then, of course, our final in person in most every situation um, in Baker in room 113 on Thursday. So okay, so yeah, that lets you know the stage where we're at, where we're going, and maybe if there are any questions about administrative issues, now would be a great time to raise those questions.
For the equation sheet, are we allowed to put any example problems or is it just for equations and formulas?
You can write anything you want to on one side of that note sheet. Some folks have put prayers. I mean, I don't think that would have been my style, but whatever. You do what makes sense to you. But as you suggest, worked out examples might be a good call. And when you do turn in the test, I'll be asking you to turn in that note sheet. And if you want to come by and pick it up later, that's great. But I always like to look at what students put down on their note sheets because if there is a common error across the whole class on the note sheet, like if you all wrote down something that's wrong, but it's always the same. It could be the case that I made a huge mistake and I would want to take that into account, certainly to not make that mistake again in the future, but also if it's depending on the nature of the mistake, I might want to adjust the grading process. I don't think it's likely to happen, but I want to be careful. Okay. So yeah, I'll have you turn those in and you can pick them up later. So I think I answered your question pretty thoroughly. Would you want to follow up?
Yeah, sounds good. So you said we can write on both sides of the one sheet of paper?
Yeah, 8.5 by 11, both sides. Yes.
Okay, sounds good. Thank you.
I think a common thing that some students do for a note sheet for the final is maybe have columns. Okay. One column could be for like the name of the method. It's going to be a pretty narrow column. Another column could have like a setup, a commonly seen setup where that would have been an example, like an example of this problem. Sort of like quantitative explanatory variable, quantitative response. You'd think regression. And so, depending on the context, there could be help there. State a null and an alternative hypothesis, or perhaps if it's a confidence interval, something else. And then maybe another thing could be good. Oh, the equation for the test statistic or the equation for the confidence interval that corresponds. Some people have confidence interval in equation one context, hypothesis test statistic, a different column. Okay. And then maybe a worked out example. So there are a lot of different ways of doing it, but using your space carefully where you can find what you're looking for is probably pretty important. Okay. Great question. Someone else want to follow up with an administrative question? Okay. Then what about questions from last time and then homework problems due today?
Can you explain why chi-squared doesn't require it to be normal, the population to be normal?
Okay, yeah, great question. Chi-square is in the context where your response variable is categorical. You're a this or a that. Or maybe there's three different types of outcome. And and so like you're an A, a B, or a C. And you might be right that underlying that there may be an actual distribution. We chunk them into A's, B's, and C's. Like letter grades are often A's or B's or C's, but it's based on, an underlying numeric score. Okay. Um, but because it's categorical, okay, you remember that it follows things like the binomial distribution. You could flip a coin, you either get heads or tails. And you might be spotting quite reasonably that with a large enough number of trials, for any reasonable rate of success, you will have an approximate normal curve from that percentage of heads. Okay, even if the underlying true population, the rate of heads is only 10%, as long as you flip your coin like 100 or more times, the distribution of the sample percentage will follow a normal curve pretty closely. Okay. And so if that's the case, there is an underlying normal curve somewhere in chi-square, but the way we emphasize things is focusing on the categorical nature of life. So because we're trying to say if categorical, then do chi-square, we try to obscure the underlying normalness of the distribution of the possible percentages. So I think I tried to answer the question in two different ways, but would you want to follow up at all, please?
That makes sense. And also for chi-squared, is the response and the control variable both categorical?
For chi-square, the response and the explanatory variable would both be categorical, yes. Which I guess we haven't talked about a situation where the response variable is categorical, but the explanatory variable is quantitative. That literally is a method called logistic regression, and it rarely comes up in Stat 312, but we hope to prepare you with enough content that when someone does spring a logistic regression on you later in life, you'd say, "Oh, well, it looks sort of like regression," and you can sort of feel comfortable utilizing the method. But there are other classes where that is covered more in depth. So yeah. Quantitative, categorical, those are helpful things for determining what is the right method. Someone else want to follow up with anything? Okay, so what I'd love to do then is to switch gears and maybe give you an example of a data set where it's going to correspond to the problem of the day, and I'm going to walk my way through um, the essentially the context of the problem and start into the method of analysis. Then we'll go back, double back, and then hit on, okay, here are the nitty-gritty details of this analysis method. I think where's his class data? And the data set I believe is named Diet and Lifespan. Let me make sure I have it. There we go. Okay, come on. Somewhere. Okay, yeah, it appeared. Zoom sucks. It appeared directly underneath my Zoom window. Okay, so that I didn't see it at all. Okay, so here we go. Here are data on the lifespan of a collection of rats, okay, and they were fed different diets. The belief in the 1980s is what you eat may have something to do with how long you live. Okay, and we gave these rats different diet treatments. It was an experiment, so they were randomly assigned to receive either NP, regular Purina rat chow, and they could eat as much as they wanted. N/N85 is they were restricted to the number of calories being 85 calories per gram of body weight. Okay, that's why the 85 number. And low protein. Well, that's another diet, a low protein diet. N/R50, R for a reduction in calories to 50 calories per gram of body weight. NR NR40, oh my gosh, that's restricted to calories, 40 calories, less than half what's optimal. RR50 is reduced calories both before and after weaning. And the low protein were like the NR50s, but in a low protein rat chow form. Okay. You sort of think how long you live depends on what you eat. What you eat is categorical. There's several different categories, okay? And then how long you live, that is quantitative. Okay. The way I would probably explore the data graphically with Graph Builder here is just how long do I live? That's on the y-axis. That would maybe depend on what you eat, the treatment. Oh, and it looks as though across these different diets, some of the diets, like this NR40 diet, seems to have a longer length of life typically than the NP diet. In fact, the maximum length of life for the NP diet is below the 25th percentile for the NR40 diet. So it seems as though this is lower. This is maybe a little bit lower, maybe lower, and then some of these are higher. At least one, two, three, four seem in the higher category, and one or two in the middling category, and certainly one in the lowest category. Okay. And so the question, does what you eat, if you're a rat, impact how long you live? My gut feeling is the answer is yes. Okay. Yay. We have learned so far that if we just use this analyze fit y by x, you can generically say, well, what y lifetime may depend on the other thing, treatment. Does lifetime depend on treatment? I don't know if it will work. I'm just taking a gut feeling guess that the answer is yeah, because like this little corner, this lower corner, seemed to just select this thing called one way, as opposed to when we had quantitative, like this guy got highlighted, or most recently with chi-square, this categorical contingency thing got highlighted. I'm just going to click OK. Stuff happens, and of course appears below the Zoom window. What happened was this. It shows me the same freaking graph. I get no new information here, but what I've learned with GMP is always go look for the little red toggle thing and it says turn on something or turn off something. Well, if I showed you the means and the standard deviations, you'd sort of think if I have one, two, three, four, five, six different groups, and I tell you the number of data points, the average, and the standard deviation of each of these six different groups, yeah, we could do a bunch of t-tests. Because if I tell you n, X bar and S and X bar and S, we could compare these two top groups to each other. Yes? Yes. Yeah. So I'm thinking if I've got six different groups, I'll call them A, B, C, D, E, and F. Okay. I could compare diet A to diet B. That's one comparison. A to C, another t-test. I could compare A to D, A to E, A to F, B to C, B to D, B to E, uh, C to D, C to E. Um, okay, so A to B, A to. Okay, so I could go through all the list. If I were being careful when I had said those things, I wouldn't have skipped a couple. ultimately, we end up with 15 separate comparisons. Compare the first to each of the remaining four, the second to each of the remaining three, the third to each of the remaining two, the fourth to each of the remaining two, the third to each of the remaining three, the fourth to the last two, and then the fifth to the sixth. That's 15 separate comparisons. I could do 15 t-tests, and I could get 15 p-values to tackle the issue um, of, are any of the groups different from any of the others? Are any of the means different from any of the others? And that would just take time. Here's the problem, though. Um, you might have noticed that there's every so often a false positive when you do a t-test. Could you ever, just by luck alone, think that there's a difference between two groups' means when in fact the two populations have the same mean? Could that ever happen? The answer is yes. How often does it happen? Yeah, 5% of the time. The number that we compare our p-value to, sometimes we call that alpha, the level of the test. Alpha, if typically 0.05, and that's the one we recommend you use, says in 5 out of 100 times, even if the two true population means are the same, we'll falsely think there is a difference. So if I'm doing 15 separate t-tests, 15 separate comparisons of two means, and if 5% of the time I make a type 1 error, it's up to 15 times 5, 75% of the time, I'm going to be making a mistake. Even if there is no difference across any of the diets from any of the others, I'm pretty darn likely to make a mistake. So we probably shouldn't do a whole collection of t-tests. What should we do? Well, that's the topic of the day today, analysis of variance, okay? Literally, if we do turn on this thing called ANOVA for analysis of variance, AN for analysis, O of VA for variance, it somehow just gives me a p-value. We have yet to talk about how this F ratio is determined, but that is the test statistic. But with the p-value that's tiny, less than 0.001, it says we reject the null hypothesis. We should believe the alternative. So we know what to do. We just haven't talked about how the method works at all. So let's go ahead and do that right now. Okay, so in analysis of variance, we have to really start with what the hypotheses are, and I'm going to sort of go with let's go with a model that we have k different populations. So there's population 1, there's population 2, population 3, up to population k. Okay, and in each population, there's a mean, mu1, mu2, mu3, all the way up to mu for population K. And I'm going to say, okay, in addition to that, we also have a standard deviation. And I want to emphasize the method here requires the same standard deviation in each of the K separate populations. So there's only one number out there called sigma. One standard deviation, sigma, K separate populations. And this is a method which arguably could be useful if we have populations where you know the population standard deviation is identical. So think lengths of life of rats. That's probably about the same spread, whether they're eating a horrible diet or a really good diet and living a very short time or living a long time, as long as I'm willing to assume that all of the different population mean standard deviations are identical, then we're home free. So we're going to get a sample from population 1, and I'm going to get X bar 1 from that group, and literally S1 as well. And I guess a sample size N1. I get a sample size N2 from population 2, and I get X bar for group 2, and a standard deviation S2. You might be thinking, hold on, didn't you just tell me the population standard deviation sigma were all the same? Yeah, we have to assume that, but I don't know what sigma is. It's a lowercase Greek letter. You don't know those things? but I do have two separate standard deviations, S1 and S2, and shoot, I'm going to have a third sample of size N3. I get X bar 3 and S3, and all the way up to get a sample of size NK from population K. I get X bar K and standard deviation SK. So we have this setup where we're going to collect data from the K different populations. What would be the hypothesis we could test? In analysis of variance, our hypothesis is mu1 equals mu2 equals all the way up to mu k. All K populations have the same population mean. On the other hand, not that. There's actually a wide variety of ways that you could phrase the alternative hypothesis. You could say at least one of the populations has a different mean than do the others. You could also say at least two of the population means are different from each other. And you're sort of thinking to yourself, okay, what if K is 2? Wouldn't a t-test be something you could do? The answer is yes. And if you're willing to assume that the two standard deviations is the same, you could do a pooled t-test, which, well, shoot, you could also do an ANOVA. But if you have more than two population means that you're comparing, by comparing the more than two sample means, okay, you should use the analysis of variance approach. That is the method that we should be using. I guess the alternative hypothesis could be also phrased that there is a relationship. There's a relationship between what group you're in and what the mean is. Oh, that's a horrible word. MEAN. Yes, sometimes it will look like that. There's a relationship between what group you're in and then the average. So if the null hypothesis is true, or if the null hypothesis is false, we have to come up with a way of measuring how close the sample data are to the hypothetical null hypothesis that you should be seeing. So how would we do that? Okay, I'm going to suggest the following. Let's come up with just a way of comparing the means to each other. And so my null hypothesis, I guess the test statistic. Now, I'm not gonna sort of like go into all the details of the test statistic just yet, but I'm gonna sort of talk about a natural test statistic that we could use, okay? And the test statistic is what I will call the sums of squares between the treatments. The sum of the squares between the treatment groups, okay? So let's go ahead and give you the definition of what that is. And this is a definition which may be a little bit different than the way our book phrases it, okay? But I'm going to sort of just go with what's commonly used. It's NI, the number of data points in the ith group. So I guess I goes 1 up to K. Uh, X bar for group I minus X bar squared. Okay. Yeah. So that looks interesting. It looks like we're comparing a group mean to something. Okay. Here we're comparing the group mean to something that looks sort of like X bar, the average of the averages, if you will. X bar is sometimes called the grand mean. In this case, I'm going to just say it's equal to summing Ni times X bar for group I. And if you ever take the sample size times the mean, that would just be the total. And we're going to divide that through by Ni, the sum of those values. Okay, so that is basically think the average across all the data points. The average across all the data points. It is the grand mean. Okay, so it's an estimate of mu if all the means are the same. All mu1 equals mu2 equals all the way up to mu k is some common value mu. If all the means are the same, the grand mean, x bar bar, is an estimate of that. So what we're seeing here in the interior of our test statistic is let's compare the group average to the grand mean, and we're going to take that difference and square it. I apologize if I erased the square or never wrote it down in the first place. Basically, we're saying how far away is this group from the average? And we're going to square that difference. And we're going to multiply that by the number of data points, and they'll be called sums of squares treatment. So let's consider the two cases. If the null hypothesis is true, I guess if mu1 equals mu2 equals all the way up to mu k, okay, x bar 1, which is approximately equal to mu1, and x bar 2 would be approximately equal to mu2, is going to be approximately equal to mu k. All the sample means should be about the same. If the null is true, that the population means are identical, then the sample means should all be very close together. Okay? So if the sample means are close together, they should also be close to the grand mean. The grand mean is basically an average of the averages, if you want to think about it that way, a weighted average of our averages. So if the null is true, this number here will be small. And if you square small, it stays small. Even if you multiply by n, ultimately, if the null is true, SST, sums of squares treatment, is small. So SS treatment tells us how far the means are away from the grand mean, the average of all the data points. And if the null is true, we have SST being small in size. What if the null is not true? Well, I'm sort of thinking if individual group means are far away from each other, like we saw in our data set, okay? If the group means are not close together, if x bar 1 and x bar 3 aren't near each other, if the null hypothesis is false, SS treatment is big. So some of you are wondering, big versus small, that's a relative term, and the answer is yes, it is. We have the sum of the squared treatments, okay, being small-ish when the null is true, bigger when it's false. And what differentiates small from big? Great question. Well, let me remind you of our test statistic T, and this is like dating way back a couple chapters. T is to test the hypothesis whether two population means are the same. We had x bar 1 minus x bar 2, yeah? Compared to 0. Over what I had was S1 squared. Let me erase that and start over again because that should be clear. S1, no, S1 squared over N1 plus S2 squared over N2. Okay. What we have is a natural way of measuring how close the means are to each other or how far apart they are from each other, divided through by something that effectively standardized them and put them on a t ruler. It allowed us to use the t distribution as our ruler to get a p-value. This number, the sum of squares treatment, needs to be standardized in some fashion so that way we can hit our conclusion. Okay, we're going to have to put it on a common ruler. Okay, so shoot, here we go. Okay, and what will that common ruler be? Okay, so I'm going to say our test statistic itself, we're going to call the F ratio. F is equal to the sum of squares treatment ni times x bar I minus x bar bar squared over then k, the number of groups that you're comparing, minus 1, divide through by ni minus 1 times si squared over then the sum of ni across the k different groups minus k. So you're thinking, that is not an equation that I ever want to have to remember. And I'm thinking to myself, me too. But if my grandma could remember this, you could. Okay. I'm not saying write down in your cheat sheet. I'm just saying this is mathematically the equivalent, okay, of the equation our book sort of provides to us. Okay. Our friend here, SS treatment, is divided through by what we'll be terming degrees of freedom treatment, treat, T-R-E-A-T. And in the denominator, we're also dividing through by, I'm going to call this SS error, and that term, degrees of freedom for error. It's just things with S and N, just like in the denominator of our test statistic T. I guess I could even take this part here, which I'm going to circle in pink. I could move that into the denominator. Heck, it's in the denominator of the numerator. Shoot, it's going to be in the denominator in some fashion. We're taking our sums of squares treatment. Undo that. There we go. We're taking our sums of squares treatment, okay, our natural test statistic, and we're standardizing it, putting on a common scale that we could use with just one of those distributional tables. And the distributional table is effectively allowing us to compare the numerator, which I will call mean square treatment, to mean square error. The whole numerator, as we have shown you before, have shown you, she's, this numerator term here, the sums of squares divided by degrees of freedom, we'll call that mean square for treatment. And the whole denominator, SS error over the degrees of freedom for error, we will call mean square error. And interestingly enough, if the null hypothesis is true, the expected value of mean square treatment is sigma squared. And if the null hypothesis is false, the expected value of mean square treatment is greater than sigma squared. But always, here's a cute little fun fact, always the expected value of mean square error is equal to sigma squared. And so what we have is this in this F ratio, and let's choose a different color for emphasis. In my F ratio, I've got the ratio of something which tends to be equal to the denominator if the null is true. And it tends to be greater than the denominator if the null hypothesis is false. So our F ratio tends to be about 1 plus or minus a little bit. If the null is true, it tends to be larger than 1 if the null hypothesis is false. So you're thinking to yourself, yeah, Steve's grandma could do this. You're thinking, you can do this. Let me show you one other fun thing about the analysis of variance table, the ANOVA table, if you will, the thing we showed you inside JMP. There we go. Notice here in this analysis of variance, and how do I do this? Okay, I unfortunately cannot make this bigger, or can I? I'm trying to sort of figure out a way of blowing that up. Oh, maybe I could do this. No, I can't do it over here. Okay, so I'm saying we have a whole table. That F ratio is just the resulting end of a collection of calculations, and we do get a p-value from the probability distribution calculator, or an F table, if you will, I want to sort of walk our way through what these various different terms are. I mentioned them already, every single one of them, in our discussion, but let's make sure that we understand the table as a whole. And the way I like to remember this is, okay, in Excel, if I adjust one cell, sometimes a whole collection of other things get adjusted. You change one number, and all of a sudden, maybe all the ones that are below it will change, or those that are off to the right will change. It's because of the way Excel does the things it does so brilliantly. Okay. This analysis of variance table has that characteristic. There's some things that when you change them, they change all of the things that follow from. Okay. And the reason why we have this analysis of variance table is the guy who invented it, R.A. Fisher, decided, I've got a whole bunch of calculations I'm trying to do. I'm working at home by candlelight at night, okay, in the early 1900s on data from agricultural experiments in England. And there's a lot of work to be doing any one of these calculations. I mean, shoot, the sum of squares, SS treatment, it's what? The sum of Ni times X bar for group I minus X bar bar squared. Yeah, if I make a mistake any one of those places, I'm going to have to sort of go back and fix a lot. Okay, and shoot, that's even better than some of the other numbers that you're going to have to calculate. I'm just saying you've got a collection of numbers that if you are well, okay, another analogy I like to use is that high school physics class, yeah, where you did this experiment where maybe you lift a weight on a string and you pull it out and you drop it and it flies down and hits a small box and knocks it a few feet and you measure how far did the box fly after you hit it with the weight attached to the string, and you tried various different lengths of string or perhaps various different weights, and you're coming to terms with characteristics of physical properties, okay? So we're doing physics, but you had a whole collection of calculations that were on like one sheet of the notebook, the lab book. And then the next page had another whole set of calculations. And you basically summarized the first page with just one number. And the second page was summarized with yet another number. The third page had a third number, fourth page had a fourth number. And finally, in the fifth page, you put all four of those together to get your conclusion. Okay. The ANOVA table has that characteristic as well. So let's talk through the ANOVA table. You can notice that it says source of variability here. Okay. So in the table, you always have a source. And it's between the treatment, TTT for treatment, or it's within the treatment or error. And there's a total amount of variability. Okay. There's a number out there called degrees of freedom. It's just the number of groups minus one. Okay. The total degrees of freedom is the number of data points. And I'm going to call that N star for now. N star is just a quick way of writing the sum of all the Ni's as we go. I goes one up to K. Okay. So we're summing up the sample sizes for each of the different groups. Ni minus one is the total degrees of freedom. N star minus K is the degrees of freedom associated with error. And you can spot that the sum of the degrees of freedom between the treatments and the degrees of freedom error add to the total degrees of freedom. Okay. The next column over here is a sum of squares. Okay. And as we told you before, there is an equation for a sum of squares between the treatment groups. It's summing across the K different treatments, and I times X bar I minus X bar bar squared. And the sum of squares attached to error would be Ni minus 1 times Si squared. And that whole thing will sum to the sum of Xij minus X bar bar squared across I and J. I is the way we denote or enumerate the number of groups. J is the way we tell you the data point within a group. Basically, summing across all of the different groups, find the standard deviation. Yeah, literally, this SS total divided through by N star minus I, or N star minus 1. Um, and a root of that, that is the standard deviation of all the values. Okay. So this is a measure of spread. The SS total is a measure of spread of the data. Here's just how far are the data spread apart from each other. Okay. How far are the data points apart from each other? And that's sort of like a way of measuring, well, how far are the groups away from each other? That's what we're sort of measuring there. And then how far are the data points away from their group average? That is our sums of squares between the treatments. Now, I chose to do this on the wrong side. I apologize. I'm hoping that you are forgiving as people, and I'm going to move over here off to the left and continue my next column, and I'm going to call it mean square, but I'm going to draw it way the heck over here. So in the mean square column, we're going to have just the sums of squares divided by degrees of freedom, and sums of squares divided by degrees of freedom. So there's the mean square treatment, MS treatment, and MS error. And finally, in the last column, or penultimate column, we get the F ratio, which is MS treatment over MS error. Okay, so the F ratio is just the ratio of those two last beasts. So in our case, I would say our sums of squares treatment is like 12,700 divided by 5. That's again, I mean, shoot, 2,500. Yeah, check. 15,300 over 300. That's about 50. So check. That 12,700 plus 15,000, that sums to 28,000. Check. 5 plus 343, check. 348. Okay, so we're home free here. Other than the mean square between the groups, that's 2,500. Divide that through by 50, I get 550 again. So that's the F ratio. Check, check. So my F ratio here has an F value 57 and a P value less than 0001. How could I get from an F ratio to a P value? That's where our friendly probability distribution calculator comes into play. So let me download that and use that to quickly show you what you would need to be able to do if you had to do it on the final, which I'm writing the final so you don't have to. Okay, so go ahead and open that. So if we have this F ratio of, okay, F ratio of 57.1043, we know the distribution is called F. Okay. Numerator degrees of freedom, 5. Yeah, so we don't have to adjust that. Our denominator degrees of freedom is 343, so I got to put in the 343. Boom. And then this is the distribution of what could happen if the null is true. You can see 1 is sort of like an average, okay? About 58% of the time you're below average and 42% of the time you'd be above average. But our F ratio was 57. How likely is it that I'd see a 57 or higher? Let's adjust to the or higher category and plug in my 57.1043. And that happens like never. I'm spotting here the values that are even looking possible are all less than 4. So the chance of being 57 or higher seems really unlikely. And the way I'd phrase this is reject the null hypothesis, because if in fact the 1, 2, 3, 4, 5, 6 population means are all identical, I should never see as much of a departure between these group means as they are departing from each other. Again, our F ratio says how far are the group means away from the grand mean, and take those differences, square them, and then multiply by n, sum that up. That sums the squares. I'm saying there's about a 0 chance that I would see a sum of squares between the treatment groups of 12,700 or larger. by luck alone. There's less than a tiny chance of seeing an F ratio of 57 or higher just by luck alone. I have to conclude that there's a difference between the population means, because if there was no difference between the population means, I should effectively never have seen what I really did see. So that's where we're going to sort of say, check. There's a lot of details in today's content. There's a whole new context, but think multiple groups, compare the means. And then we're going to have to come to terms with what these things are, the sums of squares between the treatment groups, the sums of squares total, mean squares, degrees of freedom. The lab will walk you through those, and the homework will get you feeling comfortable with that. And what we're going to do tomorrow is say, okay, cool. What if the groups, we do determine that there's a difference in at least one of the means from the others? If the population means aren't all the same, we're saying here at least one of them is different. Which one's different? You'd sort of think NP is likely to be differing, but is low protein noticeably different than the NR40? I do not know that. We will find that out tomorrow. And then we're going to talk about what if you have two factors in an analysis of variance that you want to both check out to see whether they're statistically impacting the response. Not just this one factor. What if you have two or more? But that's a topic for tomorrow. So what I'm going to do, like normal, is to stop the share and sort of say, if you got any questions, I hopefully can answer. So if you have any questions, now's time to ask them. We got a few minutes. Okay. I'm not seeing any questions, so I'm going to stop the recording. But again, I'm going to hang out for a few minutes. If you have any additional questions unrelated to